Okay, we're gonna get started. We were talking about chapter 8, which was gases. We made a pretty good dent into it. Remember that there are certain units associated with gases. The three sort of popular ones are an atmosphere, and that is equal to 760 millimeters of mercury, and that's equal to 760 torr. And remember that 760 number is an important number, as it is the one that will convert you from millimeters of mercury and torr into atmosphere, back and forth. Remember that a millimeter of mercury and a torr is essentially a 1-to-1 conversion. So they're equal to each other. We talked about some gas laws, and remember that pretty much all gas laws, all pressure, volume, temperature, is essentially what all sort of detail with. We talked about our good friend Boyle. That was a P1 V1 equals P2 V2 situation. That is at constant temperature in that case. Remember, pressure and volume here really could be any units you want, as long as they're the same on both sides, so everything cancels out correctly. Remember that as the pressure goes up in this case, the volume will go down, and vice versa. We talked about Charles' law. He dealt with volume and temperature relationship. V1 over T1 is equal to V2 over T2. This is at constant pressure in this case. And remember here, volume again can be any unit you want, but we do need to be careful. Pretty much with all gas laws and temperature, it does need to be in Kelvin. So as we talked about last time, pretty much any gas law that you're using, and if you're using temperature in that gas law, you got to put it in Kelvin when it goes into the gas law equation. There was Guy-Lussac's law, and that dealt with pressure and temperature. P1 over T1 is equal to P2 over T2. This would be at constant volume in this case. So what we saw with Charles' law was, as the temperature went up, so did the volume. It increased, and as the temperature went down, so did the volume as well. It also went down. And that's really how, in sort of Charles' law relationship, it's able to keep the pressure constant. So the volume really adjusts to allow the number of collisions that's going to occur as the temperature changes to stay constant. As we increase the temperature, we would expect gas molecules to move around a lot faster. And obviously, as we lower the temperature, we expect the gas molecules to fly around a lot slower. And in the situation with Guy-Lussac's law here, it's at a constant volume, which means as you do increase the temperature in that situation, because the volume is fixed, it will not move. We will actually see more collisions occur, and the result of that is we will see the pressure start to go up. So as the temperature goes up there you go. We do see a rise in the pressure as well, because that volume is fixed, and vice versa. If we lower the temperature, everybody's going to be flying around a lot slower. Going to be less collisions that's going to occur, and we will see the pressure start to come down. So as the temperature decreases, the pressure will also decrease in that relationship. We also briefly talked about our good friend Avogadro. There was a lot of moans at that point. And that is V1 over N1 is equal to V2 over N2. And this was actually at two things: constant temperature and pressure. So as the volume sort of increases, so is the number of moles, and that's what N is in this equation. N is the number of moles, and V is volume. And again, in this situation, it could be any unit of volume, again, as long as it's the same on both sides. Kind of putting all four of these together gave us the ideal gas law, which is a little bit different than some, and that is PV equals nRT. And remember that ideal gas law is sort of in a lot of cases, sort of a one situation. You have one pressure, one volume, one temperature, not two of everything. And it's also the most restrictive in terms of units. Pressure needs to be in atmospheres when you're using it. Volume needs to be in liters. N should be moles, and T should be Kelvin. And the reason they all need to be in those units is really the value of R. And R is the gas constant, which is 0.08206 liters times atmosphere, Kelvin times mole. So this is a constant value that you always have. Remember that you could also use 0.0821, which a lot of people will use these days. But in a lot of cases, it will not be given to you in the problem. So it's just assumed that you have that sort of number available to you. So very rarely in a sort of an ideal gas law problem will they actually just straight out say, hey, the gas constant is this. Again, it's just sort of a number that you should know that you always have sort of available to you. We also talked about a couple of things like STP, that stands for standard temperature and pressure. And remember that when you do have something in STP, it actually does sort of represent actual numbers. The temperature means that it's 273 Kelvin and the pressure is 1 atmosphere. So somebody says this is occurring at STP, those are the two values that you would use in that particular case. And there is a nice relationship that will sometimes allow you not to necessarily have to use the ideal gas law. And that is when you are at STP conditions, 1 mole of any gas will equal 22.414 liters. Again, it has to be at STP for you to use that as a conversion factor. If it's not at STP conditions, you should never use that conversion factor. You should always use the ideal gas law. As we talked about last time, you could always use the ideal gas law regardless of the conditions. If it's STP, non-STP conditions, it doesn't matter. You could just put the numbers into the ideal gas law and solve it, which is in a lot of cases maybe the best move so you don't use this conversion incorrectly. But if it is at STP, you can use this conversion and not have to use the ideal gas law. We also talked about, I think, the combined gas law. And the combined gas law is P1 V1 over T1 equals P2 V2 over T2. Once again here, like all other gas laws, temperature needs to be in Kelvin. Obviously here as well, it needs to be in Kelvin. Pressures, it doesn't matter the units as long as they're the same on both sides, and also the volume, same deal. It doesn't matter as long as they're both the same on both sides. We also talked about at the end the idea of partial pressures. And remember that when you do have a mixture of gases, each gas is basically going to contribute to the overall pressure. And that means in that situation, the total pressure is equal to the partial pressure of, say, gas A plus the partial pressure of gas B. Maybe you got a gas C in there, however many gases you got going on. So these are what are referred to as partial pressures because they each contribute to the overall pressure of the mixture in a particular container. One of the ideas of something being an ideal gas, maybe. The reason that something is sort of considered an ideal gas is one major aspect of it is there is no sort of attractive forces or repulsion forces between gas molecules when they're in a container together, the sort of ideal conditions. So what that means in a sort of partial pressure situation, we could almost treat each gas that's in that mixture kind of separately, like they're in there by themselves. And basically the common way to figure out the partial pressure of something is actually just to use the ideal gas law and solve for each of the gases individually. So you would do basically, in this example, 3 calculations, one for A, one for B, and one for C, using the ideal gas law. Remember that because they are all sort of in the same mixture, the temperature and the volume for all the gases will be the same because they're sitting in the same container. So really the only difference that you would have in this calculation would be the moles of each gas. So the moles of each gas would most likely be different. but the temperature should be the same, the volume should be the same, and R, which is a gas constant, should also be the same as well. So you basically would do 3 separate ideal gas law sort of calculations if we were doing it for all 3 of those gases. And then to find the total pressure is nothing more than just simply adding those values together. So you would just add all 3 of the pressure values together, and that would give you your total pressure. Any questions on that stuff we talked about there? Remember as well, when we talked about sort of these formulas, we talked about the idea that really if you want to pretty much have at your access all the equations that you would need to know, really sort of these 2 are really the most important ones to sort of know. Again, as we talked about, I think at the end, you pretty much could just scratch out anything from the combined gas law that's not mentioned or held constant, and you would have all the other gas laws that you would need. Again, if you didn't need temperature, you could scratch that out, and that would be Boyle's law. You know, if you didn't need, or there was no mention of a volume, for example, you could scratch that out, and then you have obviously Guy-Lussac's law. If there's no mention of pressure, you could scratch that out, and you have Charles' law. So that one right there, pretty much just get rid of whatever is constant, whatever is not mentioned, and you'll have probably the right gas law that you need by just having that one sort of gas law. Obviously, anything else is not like a 2-1 situation, 2 pressures, 2 volumes. The ideal gas law would probably clean up any other calculation that you would need to do in that particular case. Any questions on any of that stuff there? All right, so at the end there, you were working on a problem. I think we were going to start with this one here. So this is the one where we do have a mixture of gases. So in this particular case, we pretty much have 2 gases flying around. We got some helium, we got some neon flying around, basically in the same container. So the volume for both of those gases is going to be 2.5 liters. The temperature for both of those gases will also be 27 degrees Celsius, since they are sitting in the same container. We already know, since it is a gas law and its temperature, I should convert that into Kelvin. So we'll add a 273 to that, and that would get us 300 Kelvin. We are looking for the partial pressures of both helium and the partial pressure of neon in this case. And remember that we always have R, which is a constant. So we always have this number here. So if we think about it, we have a P, a V, a T, and an R. Really, the only thing we're missing to help us solve this is actually N, and that is where the grams come into play here. So we know the grams of each of the elements that are present. So we again could use the molar mass from the periodic table to do that conversion. So if we convert 5 grams of helium using the molar mass from the periodic table, that is 4.003 grams per mole of helium. And that would get us 5 divided by 4.003. Could give us a 1.25 moles of helium. We'll do the same thing for neon. That's 5 grams of neon in this case. Once again, if we go to the periodic table and look at neon, it is 2018, I believe. So 2018 grams per mole of neon. Again, that's coming from our periodic table. That's going to be 5 divided by 2018. Going to give us a 0.248 moles of neon. So at this point, we now have the moles, and we really have everything that we need to go into the ideal gas laws. So once again here, we're basically just going to do 2 separate calculations, and that's sort of the beauty of it being an ideal gas. Even though they're in the same container, there's no interaction between them, so we could just basically take one at a time here. So we'll start with the pressure of partial pressure of helium. And that would be, again, nRT divided by V. So we're going to put our values in here for helium, which is 1.25 moles. The gas constant obviously is a constant number. Our temperature that we converted to Kelvin, all divided by our volume, which was already in liters. So we're all good on that. Liters will cancel, moles will cancel, Kelvin will cancel. And that's going to give us a partial pressure here for helium of we'll call it a 12.3 atmospheres in this case. So that is considered the partial pressure of helium. We're pretty much going to do the exact same calculation here, but we're just going to pretty much substitute in neon's moles. Once again, because they are in the same container, temperature and volume is going to be the same for both of them. So we will do the partial pressure here of neon, which would be nRT over V. Putting in neon's moles, which is 0.248. Once again, our gas constant is a constant number here. Our temperature is the same because they're in the same container, and our volume is also the same because they're in the same container. Once again, the liters will cancel, moles will cancel, Kelvin will cancel. That's going to leave us atmospheres, which is good, and a calculator would be better, maybe. Let's see here. 0.248 times 0.08206 times a 300 hit equals divided by 2.5. Going to give us a 2.44 atmospheres. That is what is referred to as the partial pressure of neon in this case. Yes. Any question on either of those calculations? To find the total pressure, what do I do? Yeah, so to find the total pressure, we're just going to simply add both of the partial pressures together. So our total pressure here will be the partial pressure of helium plus the partial pressure of neon. And that's going to give us a 12.3 atmospheres plus a 244, 2.44. And 12.3 plus 2.44. We'll go with a 14.7 atmospheres as our total pressure in this case. Any questions on that there? By the way, just looking at this, the major contributor to the pressure in this mixture is which gas? It is helium. Why is helium the major contributor, you think? What's that? It does have higher pressure, so it is the one causing, obviously, more pressure. But why is it causing more pressure, you think? It actually has to do with these numbers. Helium is much lighter, yes, than neon, which means it's going to actually be moving around a lot faster because it's lighter, which means it's going to cause more collisions than the slower, heavier moving neon in that case. So if you calculate the actual, what's sometimes referred to as the root mean square velocity or the velocity of each of those, you would see that helium is actually moving way faster in terms of how its velocity than neon is. And it's because of the weight there. It's lighter, so it moves faster, faster it moves, more collisions that occur. Any questions on this type of partial pressure type situation? Okay. Another very common one. I would say you did this, but you didn't do this, I don't think. So this was the one you missed out on. You didn't really miss much, just so you know. But all right, so in this situation, we have something like potassium chlorate here. And you're going to heat it up, and it will break apart into a little potassium chloride. And some oxygen gas will be generated as a result of this. And basically, as you heat this, it decomposes. Basically, it's a decomposition reaction. A little O2 action comes out through. It's got nowhere to go. It comes through here, through the tube, into this container that was previously filled with water. As the gas goes in, the water bubbles out. And you end up with this really empty space in your container, your collection container. And it's really not empty. That is actually where your gas ends up. You can't really see it because, you know, it's colorless. But that's basically where your oxygen gas will basically end up. The result of doing this, though, is we are collecting this in the presence of water. And just the process of the reaction occurring will heat up the water a little bit. And when you heat up water, you turn liquid water into basically like gas, like water vapor is referred to, kind of like steam. So as this process occurs, in addition to the oxygen, which in this case you're actually interested in, you get a little what is known as water vapor collected along the way. And in most cases, you're really not interested in the water. It just kind of came along as the process of how you collected the gas. So usually in this situation, we now created a mixture of gases. So in this case, the total pressure would equal the pressure of the gas you were interested in, which in our case would have been oxygen, plus the vapor pressure of water, which is what that is. And the vapor pressure of water is usually a value that you could look up on a table based on temperature. And in a lot of cases, we're interested in really just the gas. So we could actually rearrange this equation here, as we'll see here, maybe. And we could rearrange it and actually solve for the pressure of just the gas. So in this case, the pressure of the gas would equal the total pressure minus the vapor pressure of water. So this is sometimes what is referred to as getting the pressure of the dry gas is sometimes referred to, because you basically are subtracting off water's contribution to this, which is what you're not really interested in. By the way, in the laboratory, the total pressure would be like the barometer reading that you would take. The pressure of the room basically is where the total pressure would actually come from. So this type of partial pressure problem is not too bad. It's usually just kind of like a subtraction type of situation. But it always occurs whenever you collect a gas where water is involved. So it's sometimes referred to as being saturated with water vapor, or sometimes it will mention something like you collected the gas over water or something like that. So some type of mention of water in a problem where you're collecting a gas means that you usually will need to use this equation. You'll also usually need to look up the value of water vapor for that particular temperature and basically do the subtraction so you get just the pressure of the gas by itself. So if we look at this here, a sample of oxygen gas is saturated in water vapor at 30 degrees Celsius. And that's really the key phrase there that helps us understand that basically what we just saw in that picture is sort of what is happening. The total pressure is 753 torr. The vapor pressure of water is 31.824 torr at 30 degrees. So this is really in most cases, a table value. So a value you would go look up in a table. So to do this, this would be the total pressure would be the pressure of the oxygen gas plus the vapor pressure of water. Once again, solving for the pressure of the oxygen gas, that would then be equal to the total pressure minus the vapor pressure of water. And I thought I put a subtract. That should have been a positive there, obviously, on this one. Felt like I left the positive off of that one there. All right. So, okay. So in this particular case, we would take the total pressure, which is 753 right there. So 753 torr. We would normally look up this value in a table, and we would subtract 31.824. And if we do that, 753 minus 31.824. That's going to give us about 721 torr. And that would represent the pressure of oxygen by itself. The partial pressure of oxygen in this mixture are the dry oxygen gas. It also wants it in atmospheres. So we would want to use our conversion in this case, that 1 atmosphere is equal to 760 torr. So taking our 721 torr, doing our little conversion here, 760 torr on the bottom, 1 atmosphere up on top, the torrs will cancel. We're essentially dividing 721 divided by 760 will get us a 949, looks like 0.949 atmospheres. And again, that would represent the pressure of the dry oxygen gas in atmospheres. So this sort of partial pressure problem is not too bad. It is sort of a subtraction sort of deal. Again, the other one would be more like a ideal gas law type problem. Any questions on this one here? Yeah. It did not. So in this case, really what the temperature was there for was in a lot of problems, they may not give you the actual vapor pressure of water. So that would be obviously you would go to the table, you would look up 30 degrees Celsius, and over there would be the vapor pressure of water. So in this case, it actually is probably going to be useful for you in a lot of these type of problems if you do come across it, because they probably will just have you reference a table that's in the chapter. Usually, there's usually a vapor pressure of water in the chapter, and that's what the 30 degrees would be for. Yeah. Other questions? Okay. All right, so to finish up, bless you, these are the kinetic molecular theory of gases. Some of the stuff we've talked about, but these are some of the important parts of it. Gases consist of tiny particles, atoms, or molecules. They're obviously moving around and flying around, causing collisions. The particles are so small compared to the distances between them. The volume of the individual gas molecules are assumed to be negligible or zero. That is one of the reasons that something is considered an ideal gas, is basically that. We really look at, and as I mentioned, I think last time, a lot of problems, we'll talk more about the volume of the container the gas is in rather than the volume of the gas itself. Particles, as I mentioned, they are flying around. It is those collisions that we associate with the pressure that occurs. Obviously, more collisions, we would see in most cases an increase in pressure. Less collisions would result, obviously, in a lowering of the pressure. Particles are assumed to have no attractive forces or repulsion forces with one another. This is really the second part of this that makes something an ideal gas. And that is really why in that sort of partial pressure problem we just did there with the helium and the neon, you basically could treat them as they're in there by themselves and not worry about the other gas sort of interfering in an ideal situation. There's really going to be sort of no interaction between those molecules. The other one there, the average kinetic energy of a gas molecule is proportional to the temperature in Kelvin. You increase the temperature, you increase the energy, you get gas molecules that are flying around a lot faster. You lower the temperature, you basically decrease the energy, you get slower moving gas molecules. Again, both of those usually will have some effect a lot of times on the pressure, especially if the volume is being held constant. So we would either see an increase or a decrease in those pressures in that situation. Here are some of the relationships we've talked about with some of the gas laws. Again, higher the temperature, more collisions. Lower the temperature, less collisions. And if we are in a rigid container, that means that basically the volume will not change. It's basically fixed, so the volume will not adjust. So we will see, as the temperature increase, like we talked about with P1 over T1 equals P2 over T2, we increase the temperature, we'll see an increase in pressure. And if we decrease the temperature, we'll see a decrease in the pressure. Now in Charles' law, which is this arrangement, as we talked about earlier, Again, what allows it to basically maintain that constant pressure is the volume is not fixed. So the volume is really the factor that will adjust when you're talking about a Charles law situation. And when we increase the temperature, larger volume gives everybody a lot more room to fly around in, even though they're moving faster because of the higher temperature. It still keeps the number of collisions relatively constant, and that keeps the pressure constant. And obviously, as we lower the temperature in the Charles law situation, as we talked about, the volume will also lower down. That means our slower moving gas molecules don't have as far to go to cause collisions. And that will also keep the rate of collisions pretty much constant and keep that pressure constant as well. Any questions on gases here? Yeah. All right, that should wrap up chapter 8. So we're up to chapter 9, which should be, like I said, exam 3 stuff. And we're going to talk about solutions here. All right, so let's talk a little bit about solutions. Solutions are what are referred to as aqueous sort of substances, are really aqueous mixtures. Solutions, again, are the guys that get the AQ symbol next to them. And really, again, the difference between AQ and something that has a liquid is something with a L is just one substance by itself. A solution, which is really a homogeneous mixture, means you got to at least have two things mixed together to make a solution. So that is usually what happens. And there's really two parts to a solution that's important. The smaller part of the solution is known as the solute. That's usually the stuff that's like dissolved in the larger part of the solution, which is known as a solvent. So if we have a sodium chloride solution, the solute is always pretty much the name of the solution. So if it's a sodium chloride solution, the solute would be sodium chloride. If it's an ionic compound, pretty safe bet that the solvent, and in most cases, will be water. So water is a really good solvent in a lot of cases, not all cases, but it works really well with things that are ionic. And that's usually your solvent. So to make this solution, what you would do is you would weigh out a certain amount of solid sodium chloride or salt. You would put it in water, you would stir it around, it would dissolve, and now you would have a sodium chloride solution sitting in front of you. So again, if I had a potassium nitrate solution, the solute would be potassium nitrate. And again, probably the solvent there would be water, would be the larger part that you would dissolve in it. So this is a copper 2 sulfate solution. This is our ionic compound here, which would be our solute. Obviously, water here, which is the larger part, would be our solvent. And as we start to mix it, our solid will start to dissolve. And now we have basically ions floating around in this solution. By the way, that's pretty much what a solution is. It's nothing more than positive ions and negative ions, cations and anions, basically floating around in most cases. In some cases, you will have some stuff together, but a lot of it is those ions that are floating around. Now, as I mentioned, in a lot of cases, water is a really effective solvent. And the reason why water works really well for things that are ionic is because water is a polar molecule, which means, as we know from bonding, there is a positive side to water, which is pretty much where the hydrogens are, and there is a negative side to water, which is where the oxygens are. So when you take something like a solid sodium chloride, what happens is those sodium ions will break apart and basically get surrounded by water, and it would get surrounded by the negative side of water. That would be the oxygen side. And the chloride ions would also get surrounded by water in this case, but it would actually get surrounded by the positive side of water, which is the hydrogen side here. And that is basically how something dissolves. And it's a misconception that a lot of people have, that some type of chemical reaction is occurring when you make a solution like this, because visually we can no longer see the sodium chloride, but it's actually still there. It's just surrounded by a ton of water molecules, which means visually we cannot see it anymore. And those water molecules serve two things. They basically serve to dissolve the solid, but they also keep the two ions apart from each other. So without the water there, those two ions would come back together and you would see your solid reform. So if you had a sodium chloride solution and you put some fire underneath it carefully and you started to heat it, that's a fine Bunsen burner. It is a triangle on top of a line, but it could be a Bunsen burner. And as you would start to heat this, all the water would start to evaporate. And at that point, once all the water evaporates, there's really nothing stopping these two guys coming back together. And you would see your sodium chloride basically come back to visualization there, because it's no longer surrounded by water. We help things basically dissolve by doing what? When we are going to dissolve something, we very commonly start to stir it, right? You're stirring it, you're doing a couple things, you're adding a lot of energy, right? It's just going to help everybody kind of come apart. You're also throwing a bunch of water all over that solid, basically, and it's going to allow all those water molecules to interact with the solid a lot quicker, and obviously allow it to dissolve a lot quicker. So as you're stirring, these water molecules work their way in, and because there's so many of them, they're able to really pry apart the ionic solid. Before it gets there, this is pretty much what your ionic solid looks like, is all the ions together, the positive and negative guys attracted to each other. It's actually a really strong attractive force, and the only reason it's able to kind of pry it apart is there's really a lot of water molecules involved to allow them to kind of separate out from one another, and that little added energy as you do it. Here's another picture in case you didn't like the first picture. A third picture in case you didn't like the second picture or the first picture of that. I'm out of pictures. Sad. All right. Let's talk a little bit about solubility, though. So examples of things being soluble in water. If something is soluble, what that really means is two things. If we're talking about a solid like in a liquid and they're soluble in each other, what that means is the solid should dissolve. So kind of like the salt in the water should dissolve. If we're talking about two liquids that are soluble in each other, that basically means that they will mix and it'll just look like one liquid. You won't see different layers, basically. So if you had two liquids that are soluble in each other and you put them together, they pretty much look like one liquid. If you had two liquids that are insoluble in each other, you would see different layers happening because they won't really mix together. And obviously, if you had a solid that was insoluble in a solvent, it wouldn't dissolve. So, you know, if something's insoluble, typically it will not mix, it will not dissolve. A lot of times when people talk about sort of liquid and liquid mixing, they talk about the word miscible being soluble and something being immiscible is insoluble. So sometimes they talk about that. So definitely in water, because it's polar, any ionic compound, pretty much that's a really good solvent. It should be soluble in it. But there are things that are non-ionic compounds that are also soluble in water, things like sugar and things like ethanol. So for example, if we look at something like ethanol, it looks like this guy here. Preview of chapter 12, maybe. Now, this is ethanol here, and this is what it looks like. And what ethanol actually has is kind of two parts. It has this part here, which are all carbons and hydrogens. And based on what we talked about with bonding, that is a non-polar part of the molecule. But it does contain this part here, which is an OH group, which is a polar bond. And the oxygen is partially negative. The hydrogen here is partially positive based on the difference in electronegativity values. So the difference in electronegativity values tell us that the oxygen is going to be more negative. So because it does contain this OH group, that allows it to work really well with something like water, which, by the way, also has the identical bond there. It has the O and the H bond, which is also a polar bond. So they get an attractive force between one another, which is known as an intermolecular force, where the positive side of one is attracted to the negative there. And that allows something like ethanol, although it's not ionic, to be soluble in water because it's relatively small. It has this little group there where it could interact really well with water. And this is, by the way, what is known as hydrogen bonding, which is what is referred to as an intermolecular force. That is the force that holds basically one molecule together with another, basically. And hydrogen bonding is a pretty good force. Sugar, on the other hand, is a little bit bigger of a molecule, but pretty much we'll see a picture here in a second. Sugar is pretty much littered with OH groups everywhere. So everywhere there's an OH group, it allows water to interact with it, and it makes something like sugar really soluble. As you might know, if you've ever put sugar in water, it should dissolve, right? And it makes it really soluble because of that. So here's an example. This is methanol. It also has, again, this OH group that's able to interact with the water through hydrogen bonding, and it makes something like methanol also soluble in water. Again, it's not a really big molecule, so it's able to interact well with water. And there's our ethanol interaction. Now, when we talk about oil and water, do they mix? And the answer is they really do not. And that's because the carbon-hydrogen bond, if you do the difference in electronegativity, it is a nonpolar bond. And pretty much oil is nothing more than super long chains in a lot of cases of this carbons attached to carbons and hydrogens attached to those carbons. I won't draw them all, but pretty much there's hydrogens everywhere and carbons everywhere. And it's a really big molecule in a lot of cases that is nonpolar. So the problem that happens when something like oil and water get together is water, which is a polar molecule, is trying to use what is known as hydrogen bonding, which is the intermolecular force there for water. And something like oil is trying to use what is known as dispersion forces, which is pretty much what oil and nonpolar molecules use. Dispersion forces are really weak forces. They are temporary forces. Hydrogen bonding is a really strong force that's not temporary. So you get this guy that's like temporarily able to interact, but over the long period of time, what happens is they do not have a way to interact well with one another. And that's why if you ever mix oil and water, right, or oil and vinegar salad dressing, right, it mixes for a bit, but eventually it will separate out. And over a short period of time, things can interact with each other through dispersion forces and have a relatively interaction. But over a good period of time, and sometimes not a really super long period of time, those forces just can't maintain that interaction and they will separate out from each other. And that's, again, like, you know, your oil and vinegar salad dressing sort of separates out, or oil and water. The other really problem with like oil and water is oil is typically a fairly large molecule. So because it doesn't have any way that interacts like water interacts with itself, and it's really big, in order for oil to mix with water, you would have to create a really big hole in the water and water sort of interaction that's there. And it really doesn't work very well. So, you know, it's kind of like if you wanted to park it like a semi truck in your garage, right? You can get some of it in, but probably not all of it, right? It's not going to fit, right? You know, so it's the same idea here. You know, you could get it to work a little bit, but over the period, it's just really too big to interact with those water molecules. So that brings up a really important idea in terms of solubility and why things are soluble in each other or not soluble in each other. And that's the idea of like dissolves like. And the idea of like dissolves like is things with very similar interactions with other molecules. If they can interact with other molecules the exact same way that they interact with themselves, they're going to be soluble in each other. If they come across another molecule that uses some other way of interacting that they do not use, they're going to be insoluble in each other. So really what that means is there are things that are typically soluble in each other And those are typically things that are ionic and polar. So those things work well. Things that are polar and polar, they work really well because they're going to use the same type of interaction with one another. And even things that sometimes people overlook, non-polar things and non-polar things are also going to be soluble in each other because they're both using dispersion forces. They're both using the exact same way of interacting. Truthfully, you really only get in trouble when you are kind of crossing over something that is polar and non-polar together. They're going to be insoluble in each other. They're really not going to mix because they're using very, very different ways of interacting. How things interact with one another are intermolecular forces, as I mentioned, and pretty much the basis of all intermolecular forces is a very simple interaction of the positive side of one molecule is attracted to the negative side of another. So polar molecules have a fixed positive side and negative side, and that means that they're always ready to go. They're always ready to go and interact, and they mix really well together. So things that are polar always has a positive side to the molecule and a negative side, which means, like I said, they're good to go. Non-polar things are pretty much neutral. They don't have a negative side. They don't have a positive side. And that's because they're sharing electrons equally over the entire molecule. So they're non-polar. So there isn't a side like in water that's negative and a side that's positive. If you have a non-polar molecule, there's pretty much no positive or negative side. So what happens when they interact, which is dispersion forces, is they temporarily can sort of gain a positive side and negative side, but it's really just a very short temporary sort of situation. And that's why they're really weak sort of forces, dispersion forces, because temporarily they could get that positive, negative, which allows them to interact. But over the long haul, they can't maintain that. And that's why they're very weak. So one way you could get like a non-polar molecule to sort of have a charge is, for example, if you rolled up next to it a polar molecule. What's going to happen with this guy with no charge and it comes near the negative side, the electrons in this guy is going to go, I want to go that way because they don't like to be near each other. And what's going to happen is that non-polar molecule, which normally doesn't have a charge, will temporarily gain a charge. And now these two guys have a way to temporarily interact with one another. But as soon as that polar molecule kind of moves away or something else changes, that guy's going to lose that charge and it's going to kind of fall apart. So over a short period of time, they can interact with one another, but over a long period of time, they cannot. But two non-polar guys that come together, that's pretty much how they interact with themselves. So they're good. They'll mix and they'll continue to interact that way. So anything that is polar and polar should be soluble. Ionic and polar should be soluble. Non-polar and non-polar should be soluble in each other. Again, if you cross over polar and non-polar, they really should not mix with one another. Any questions on that there? All right. So here's a picture of sugar up on top. So although it's a relatively big molecule, like I said, it's pretty much littered with OH groups all over. And in this case, that is going to allow it to work really well with water. Everywhere there's that OH group, water pretty much can attack it, and it makes it really, really soluble in it. Down on the bottom here is pretty much what oil looks like. And as you can see, it's all carbons and hydrogens, which makes it non-polar. So again, something like oil is going to use dispersion forces, something like water, hydrogen bonding, not the same sort of interaction. So that's basically a polar thing, water, oil, a non-polar thing. So they're going to be insoluble in each other. And that is typically what will happen is usually the oil will kind of float to the top. The water layer will float there. Now you can see this is water interacting with another water, and it interacts well with each other through hydrogen bonding. So the positive side of one water is attracted to the negative side of another water. Now let's talk a little bit about solubility. If one substance, the solute, dissolves in another, which is the solvent, it is said to be soluble in one another. So salt is soluble in water. When one substance does not dissolve in another, it is insoluble. So oil is insoluble in water. There is usually a limit to the solubility of one substance in another. Perhaps, you've done it. If you take a little bit of sugar and water, right, it will dissolve. You're waiting for your food to come at the table and you take all the sugar packets and you keep dumping them into your water, right? At some point, it may not dissolve. You take the Costco size of sugar and keep dumping it into just a glass of water. At some point, it will not be able to dissolve. So there is a limit to how much you can get to dissolve. It is usually based on temperature. Typically, if it's a solid and you increase the temperature, also increases the energy and allows a lot more solid to dissolve. And if you decrease the temperature, usually the solubility of a solid in a liquid will decrease as well. Gases are always soluble in one another, and that's because gases are constantly flying around. So as they are flying around, they are constantly mixing with one another. So gases, in the same container should be soluble in one another. Some liquids are also soluble in each other. So that's your polar liquid and your polar guy, your nonpolar liquid mixing with the nonpolar liquid. So those guys are always soluble in one another. Now, how do we know if we maybe put together a couple of guys in a reaction and two ions come together in a solution? Will they be soluble in each other? Will they be insoluble in each other? Will they make a solid or will they not make a solid? One of the ways that we could do this for ionic compounds is to use what are known as solubility rules. So solubility rules, here's a table of some solubility rules. Anything that is from group 1 on the periodic table will always be soluble. There are no exceptions here, which means if you see a formula for an ionic compound and it contains anybody from group 1, a sodium, a potassium, that's pretty much all you need to look at, and it should be soluble. By the way, if something is soluble based on these solubility rules, those are the guys that get the aqueous symbol in your formula or your equation. If something is insoluble, what that means is it will not mix and you would expect a solid to form. And those guys are the ones that get the S symbol next to the formulas. So if you use solubility rules to help you decide maybe what state you would expect it to be in, if it's soluble based on the rules, you should expect it to be aqueous, which means no solid. And if it's insoluble, you should expect it to not mix and a solid should form and would get the solid thing. Anything with ammonium, which is NH4 plus, will be soluble. There's no exceptions. So if you see anything with ammonia in it, or ammonium, I'm sorry, it will always be soluble. Nitrates are always soluble as well. So anything that in a formula that has NO3 in the formula should be in a solution, should be aqueous. Chlorides, bromides, iodines, they're soluble in everything, but there are 3 exceptions, which is silver, lead 2, and that's actually mercury 1. So what that means is if it is chloride, bromide, or iodide, it will be soluble. Should get the aqueous symbol, just like these guys. Except if it is chloride, bromide, and iodide that has one of these 3 guys. So the exception would be the opposite. So instead of being soluble, it would be insoluble if you had one of those 3 guys on the right attached to a chloride, bromide, or iodide. Sulfates are typically soluble, so anything with SO4 in the formula should get the aqueous symbol, but there are some exceptions. So anything with sulfate that is calcium, strontium, barium, or lead 2 would be an exception, and it would end up being a solid and being insoluble. When we look at carbonates, they typically are insoluble, which means they are typically things that should get the S symbol next to them. But if they had anybody from group 1, which is this guy, or anybody that's ammonium, which is that guy, they would then still be aqueous. So that's kind of the same rule as the top rule. Phosphates are typically insoluble, which means anything with phosphate in the formula should be a solid, except again, group 1 and ammonium, which again is the same kind of rule as the top. Lastly, hydroxides are typically insoluble, which means it's an S. except if it's group 1 are calcium, strontium, and barium there, then they would be an aqueous. So we could use these rules to help us understand when we look at an equation such as this here, little silver nitrate plus some sodium chloride. That's a double displacement reaction. We talked about these positive, negative, going to switch partners and make sodium nitrate plus some silver chloride. All right, so based on these rules, we could determine what state each of these guys are. So we'll start here. Although we may not see silver on the left-hand side, we do see nitrate. And we know that if we go here, nitrate is soluble in everything. There's no exceptions. So this guy should be a solution and should have the aqueous symbol next to it. If we look at sodium, and the next guy, sodium is group 1, which is the very first rule here. Group 1 is soluble, and there are no exceptions. That means, frankly, you don't need to go any further. You know that this guy's going to be aqueous. If I did go further, because I was not convinced, I would see chloride, right? And I see chloride is soluble in everything except for silver, lead, and mercury, which is not the case here. So that means it is still soluble. I see sodium, which means, frankly, I don't need to go any further because sodium is group 1, and that means it's soluble, and it should be aqueous. That means nitrate as well. If I looked at nitrate, it also is aqueous and soluble. They should agree with each other, by the way, right? So that is going to be soluble. In this case, we don't see silver, but we do see chloride. Chloride is soluble in everything except for silver, lead, and mercury, which means instead of it being soluble in this case, this would then be insoluble, and you would get a white solid that would be formed here. Maybe you did it in lab at some point. It's a common one that you very commonly do. Question on that there. So let me do another one here that you could do. Let's do lead to nitrate plus let's do potassium bromide here. Make some potassium nitrate plus some PbBr2. All right, based on solubility rules, is it aqueous? Is it solid? Fill in everybody in that equation. I know, it's chemistry. I should balance it. I know, I hear you yelling already. All right, there we go. All right, I balanced it. Stepping away. All right. Start the first one here. We got lead, but I do see nitrate. And from the rules here, I see nitrate is soluble in everything. That's pretty much all I need to know. That should be a solution and should be aqueous. I come to the next one. I hit potassium, which is group 1, which also means it's soluble in everything. There's no exceptions. Really, that's as far as I need to go. That's going to be aqueous. Here on this side, I hit potassium one more time, which is also still soluble in everything. No exceptions. That's as far as I need to go to know that it's going to be aqueous and a solution. We could also look at nitrate here, which tells us the same thing. It is soluble in everything. And lastly here, I see lead, but I see Br. So Br would be here, which is soluble in everything except for silver, lead, and mercury. And that is lead there. So instead of being soluble, that's going to be insoluble. And that would be the solid that would form in this particular case. Yeah. Any questions on that there? Bottom one, first guy is soluble or insoluble? First guy is going to be soluble here. We're looking at chloride. The only exceptions are silver, lead, and mercury, and that is none of those there. That is calcium, so this should be soluble, which would be aqueous. I see sodium, and frankly, that's as far as I need to go because that's group 1 and it's soluble in everything. So that is going to be aqueous. I got calcium here and I got sulfate. So I'm going to look at sulfate. And sulfate is normally soluble except when calcium is present. So because it's normally soluble, but this is an exception, it would be the opposite, and we would actually get a solid here formed of calcium sulfate. And lastly here, I see sodium, which once again is as far as I need to go. This is going to be soluble, yeah? Question on how to use the rules there. All right. Hey, there's the rules again. All right. So let's talk a little bit more about solutions and the idea of some other effects on solubility. We talked about the idea of like dissolves like. So again, things that are very similar in how they interact with themselves is a good way that they can interact with others that do the same type of intermolecular forces. Solubility of solute and a solvent does depend on temperature. So at a higher temperature, you typically can have a larger solubility of a solid in a liquid. In fact, sometimes what they tell you is if it's not dissolving, heat it up a little bit. And what you do when you heat it up, like I said, is it increases the energy and allows a little bit more of the solid to actually dissolve in the solvent. Lower temperature, we have a larger solubility of a gas in a liquid, and that is because, as we were just talking about, if this is my gas molecule in my liquid and my temperature is low, my gas molecule is moving fast or slow, which means it's going to stay in the liquid part for a lot longer time. Yeah. So it's going to say mix with the liquid part for a much longer time. Obviously, the opposite would be true. At a higher temperature, the liquid is going to shoot out of the liquid and not really mess very well with or mix very well with it. Solubility of a gas depends on pressure. The higher the pressure, the larger the solubility of a gas. And that also has something to do with at a higher pressure, what's the deal with my volume? My volume is low. So in a high pressure, low volume situation, pretty much everybody's sitting next to each other, right, in the container. And they're going to be mixing a lot more at that situation because they're frankly right next to each other. So there'll be a greater mixture of gases at a higher pressure, smaller volume because they're sitting and flying around in a much smaller area. Now let's talk a little bit about solution composition. There is a limit, like I said, to how much solute you can get to dissolve in a solvent. If you have too much solute dissolved in a solvent, that is what is, no, I won't say too much, but if you have really the maximum amount of solute that you could get to dissolve at a given temperature, that is what is referred to as a saturated solution. So a saturated solution is pretty much the point where you've hit exactly the most of that solid that you could get to dissolve, which means if you hit the saturation point in a saturated solution and you continue to try to dissolve something, it will no longer start to dissolve because pretty much you've hit the maximum that will dissolve. So it will just kind of pile up on the bottom, if you will, kind of like the example of too much sugar kind of added to water. What is the opposite? The opposite is you haven't really hit that point yet. So that is what is referred to as an unsaturated solution. An unsaturated solution, you haven't hit the maximum amount that will dissolve at that temperature. So that means you could continue to dissolve more solid. And you could continue to dissolve more solid until you hit the saturation point or a saturated solution. So unsaturated solution, you really haven't hit it there. Hit the maximum that will dissolve. You could continue to dissolve until you hit the saturation point. There is something that's referred to also as a supersaturated solution. And in a supersaturated solution, a very common way that you can make a supersaturated solution is you kind of dissolve something as you're heating it up. So as we just talked about, as you heat it up, right, you're going to increase the solubility of a solid in it. And what happens is because you're heating it, you're going to be able to pile in there a lot more solid, and it's going to all dissolve because it's a higher temperature, a lot more solid will be able to dissolve in it. after you heat it up and you got all that you want to dissolve, you usually just let it sit. And as it sits, this solution that you're making, it's going to start to cool down. When it starts to cool down, what happens to the solubility of everything you have dissolved in it? It actually will start to come back down with the cooling. The problem is you've already dissolved it. So as it cools back down, what happens is you still have a solution at this point, but it gets to a certain temperature and the solution goes, whoa, you got like way too much dissolved in here now that we're back at 20 degrees rather than 100 degrees Celsius. There's too much dissolved in there. So actually what you create is a really unstable solution. It is so unstable that frankly, if you just took like that amount of solid and just dropped it in there, it's going to go, whoa, too much. And all of the solid will pretty much come right out of solution. So it'll go from like the liquid state and you'll just actually see all of the solid come out of solution. It can become like really solid again. It's actually so unstable that sometimes when people do this experiment, just simply lifting like the flask and just gently putting it down is enough to cause it to just jump out of solution. It's so unstable. And that's because really in a supersaturated solution, you've ended up with just way too much solute dissolved in that much solvent. And it creates, like I said, a very, very unstable sort of solution. Another common way to describe solutions is concentrated or dilute. A concentrated solution has a relatively large amount of solute dissolved in it. We'll talk about molarity, but molarity is a very common unit of concentration. So the higher the big number next to the M, the more concentrated it is, really the stronger it is. So the lower the M value, the less concentrated it is. A dilute solution is a solution that contains a relatively small amount of solute. Most of the time in the lab, that is what you're using. They get it in a more concentrated solution. They dilute it down by adding some water in a lot of cases, and you get a less concentrated solution, not as strong, if you will. So electrolytes are substances that will dissolve in water and create ions. And because they do create ions, the presence of these ions in the solutions helps to conduct electricity. So there are a couple of different types of electrolytes. There are strong electrolytes. And strong electrolytes 100% break apart into ions. And because they 100% break apart into ions, they conduct electricity really well. So a common experiment, like I think maybe this week it is, you take a light bulb with some electrodes on it. And if you put that in a strong electrolyte solution, the light bulb would be very bright. It would conduct electricity really well. Light bulb will go off. It'll be really super bright. Something like a sodium chloride solution, which is an ionic solution, and most ionic solutions, or a lot of ionic solutions, are strong electrolytes. In solution, it will 100% break apart into sodium ions and chloride ions. And that essentially is all you got floating around in that solution are those ions. So 100% is what you have. So because it creates a lot of ions really quickly, it's able to conduct electricity really well, and that light bulb goes off very brightly. There is a weak electrolyte, which basically will stay together, but will produce a few ions And that means it could still conduct electricity because there's still a few ions. So it still can conduct electricity. In terms of the light bulb example, it would come on, but it would be very dim. So it would come on, but not conducting as much electricity. Something like hydrofluoric acid is a weak acid. It's also a weak electrolyte. When it breaks apart, it'll break apart into H plus and F minus. So in solution, it will create a few of these ions. But this is actually mainly what you have in solutions. So it mainly stays together, but it's able to produce a few ions in solution. So if you look at that solution, you mainly have the HF guys still floating around, but you got a little bit of the actual individual ions in there as well. So because it's still, again, able to produce a little bit of those individual ions, it's able to kind of complete the circuit, but not as great. And it will still conduct electricity really not as well as a strong electrolyte. You could recognize this because you typically will see ions on the right-hand side. You'll see the things still together, but more importantly, you'll see these double-headed arrows. And that's an example that it is a weak electrolyte. It means it's a reversible reaction. It means this reaction goes in the forward direction, which is going from reactants to products. And at some point, what will happen is you'll make enough products that they will decide to go back the other way, and they will recombine in what is referred to as going in the reverse direction. And that is different than in a strong electrolyte, which is basically a one-way street. Everybody is dumping off into the product side. Nobody's coming back the other way. So nobody's coming back the other way. In a strong electrolyte, it's going to 100% break apart into ions on the right-hand side. The last sort of guy, I guess, would be a non-electrolyte, which will dissolve. But no ions are formed. And because they do not form any ions, they will not conduct electricity. And sugar, for example, you take some solid sugar and you dissolve it in some water, you'll get some sugar that dissolves. But sugar is a covalent compound. It's all carbons, hydrogens, and oxygens, like we saw on the other page, our other slide. And because of that, there's really no ions. And because of the lack of ions that are there, or not there, I guess, is really why it will not conduct electricity. Any questions on that? So if you did the light bulb example, light bulb would not go off. To sort of show that, here's a picture of the light bulb sort of example. This is a strong electrolyte. You can see the light bulb goes off very brightly there because it's nothing but ions in the solution. One-way street, one-way arrow, all ions basically. This is a weak electrolyte. Light bulb still goes off, but it's dim. And that is a two-way street, double arrow, something together and ions on the other side. And this is a non-electrolyte, basically no ions. So one-way street, but the same thing on both sides and no ions are formed is how you could kind of recognize them. Any questions on that there? All right, we will lay it up there for today.